Okay, so OLS asymptotics. So far, we focused on properties of OLS that hold for any sample size. The properties of OLS that hold for any sample sizes are, the expected value or unbiasedness under assumption 1 through 4. Okay, the variance formula under assumption 1 through 5. Gauss-Markov theorem under assumption 1 through 5, right? And what was that Gauss-Markov theorem? Basically, we said that well, we have unbiasedness and we have a closed form solution for the variance, right? And then adding the assumption number 6, we have exact sampling distribution for our beta hat j, which is t distribution, right? So this properties hold for any sample size. Now we want to look at the properties that hold for large sample sizes. Okay, so for large samples, we are going to talk about consistency. So, and we say that an estimator is going to be consistent if assumption number 1 through 4, there's a prime here, for prime holds, right? And then we talk about asymptotic normality under assumption through number 1, from number 1 to 5. Look at that. We don't have assumption number 6. Whenever we are talking about asymptotic properties, large samples, there is no need to have assumption number 6. Okay. So without assuming normality of the error term, so without having assumption number 6, I can say that my beta hat j's are going to be normally distributed. Not even t distribution, normally distributed. So this is a big deal. So we're going to see that what's the trick, what's the magic, why we can say without having that normality assumption, the beta hat j's are going to be normally distributed. For that, we're going to use something called central limit theorem. And I'm going to refresh your memory from, I don't know, you should have seen this from your statistic course, but if not, I'm going to show you a visualization and basically go over what's the concept of central limit theorem and why it enables us to say that our estimators, beta hat j's, are normally distributed without making assumption number 6. So this is a big deal. This is a very big deal. And it's good news, honestly, because in practice, most of the time we are working with very large sample sizes. And I know that if the sample size is super large, then I don't need to be worried about normality of the error terms or the residuals, right? Previously, it was a big deal because if for any sample size the errors are not normally distributed, I could not rely on the t-stat or f-stat. But here we're going to say that, you know what, you don't need it as long as the sample size is large. All right. So first, let's talk about the consistency of OLS. So what is the consistency? So we are going to say that so imagine theta hat is an estimator, right? So it can be, theta hat can be equal to beta hat, or it can be equal to x bar. So remember, from the statistic course, what is the best estimator for population mean? Sample mean. What is the best estimator for population standard deviation? Sample standard deviation, right? So again, I'm saying that what is the best estimate for mu? It's x bar. What is the best estimator for sigma? It's s. Here in regression analysis, we're going to say that what is the best estimator for beta? The answer is beta hat. Okay. And we are going to say that if this condition holds for your estimator, which is beta hat, then your estimator is going to be consistent, right? What it means that, so first let's read through the theorem and then talk about it. So for this theorem, I need assumption number 1 through assumption number 4, and the OLS, we say that we're having these assumptions, the OLS estimator beta hat j is consistent for beta j, for all j's. So we imagine we have k exponential variables, right? Consistency means how far the estimator is likely to be from the parameter as sample size increase indefinitely. Okay. What is that? So let me go back and remind you of the, well, not go back. Let's open up this thing. What was unbiasedness? Unbiasedness was a property of your estimator for any sample size. We said that on average, we are hitting at a target, and this distribution is independent of the sample size. Whatever the sample size is, for any sample size, we have a distribution, an expected value of beta hat j is not dependent on n. It's equal to beta j, right? However, for consistency, we're going to say that the distribution for your beta hat j depends on n, right? So imagine this is a sampling distribution for beta hat 1 and for different sample sizes. So this is when sample size is n1, sample size is n2, and sample size is n3. And imagine we are increasing the sample size. We are increasing the sample size when we go from n1 to n3. We are going to say that the distribution of your beta hat j, so I start from here, the pale blue version, right? So the distribution of beta hat j is going to shrink. It's going to get narrower and narrower. Can you see that? It's going to get narrower and narrower as we get close and close to infinity. So as the sample size increase, so this is the definition of consistency. As the sample size increase, the distribution of your beta hat j is going to shrink and shrink. And eventually, when sample size goes to infinity, the distribution is going to collapse into one line. Okay. What's going on here? So what's the intuition behind it? Think about it. If the sample size goes to infinity, what will happen to your beta hat j or beta hat 1? If the sample size goes to infinity, it means that we're going from sample to population. If I go from sample to population, it means that my beta hat 1 or beta hat 2, again, for the population, it's going to be one number, and that number is beta 1, right? There is no distribution for that if I send that sample size to infinity. So this is the intuition. So we say that when sample size increase, the distribution of beta hat j is going to get narrower and narrower, and eventually, when the sample size is large enough, by large enough I mean is exactly equal to population size, we get to one single point, right? So this is a definition of consistency. And I want you to remember, unbiasedness is a feature of an estimator for any sample size. Again, look at this one. For any sample size, we are going to say that if you're hitting at the target or not. Consistency is a property of it involves the behavior of the sampling distribution of the estimator with regards to different sample sizes as the sample size gets larger and larger, right? So there's a difference between the two, and both of them are, these are abstract concepts, because in real world, I think I received an email from a couple of you guys that you were kind of confused, that you said, okay, in real world, we always work with one sample. So how do I know? And we always see one beta hat 1, one beta hat 2, one beta hat 3. Absolutely, this is the idea. And you ask, so how do I know that there is a distribution for beta hat 1 and there's a distribution for beta hat 2 and etc.? Well, the point is that, yes, when you're working with one sample data set from Wooldridge package, you only end up seeing one of these beta hats. One of these beta hat 1, one beta hat 2, one beta hat 3, right? So there is no distribution for beta hat 1, beta hat 2, beta hat 3. But we are going to make an assumption. We're going to say that hypothetically, imagine you are resampling from that one sample in Wooldridge thousands of times. For each sample, you can calculate one beta hat. So at the end of the day, I have thousands of these beta hats. So this means that I can plot the distribution of these thousands of these beta hats. Okay, so that's the idea. Now, when you're doing this sampling, if the sample size is fixed, we can say something about unbiasedness. But if you increase the sample size, imagine you're God, you observe everything, you have the luxury to see the full data set, let's say millions of records, and then you start with a sample size of 100 and then calculate your beta hat 1 and then increase the sample size to 1,000, to 10,000, to 20,000, to 100,000, and etc. So that's where your beta hat j, the distribution of beta hat j, depends on sample size as well, right? And we're going to say that there's a property. If you have the first 4 assumption, then it's mathematically we can prove that. It's beyond the scope of this course, but mathematically we can prove that the p-lim of theta hat n, or beta hat n in this case, is going to be equal to theta. So let's go back here. The p-lim here, the p-lim of my beta hat j n, so j is, for instance, I have beta hat 1, beta hat 2, beta hat 3, and n stands for it depends on n. As I send n to infinity, is going to be equal to beta j. So this is the definition of consistency. All right. So Now let's talk about the, uh, the relaxed version of the fourth assumption. We call it MLR4 prime. So remember, we had MLR4, which was zero mean conditional assumption. Now we don't need to have zero mean conditional assumption. We have zero correlation. Okay. Do you remember this slide? I guess we are seeing this slide from class 2 or 3, and we are at class 21 now. So this is an important one. We said that independence will lead to mean independence. This will lead to zero correlation. So here we got our zero mean independent assumption from this mean independent assumption, right? We said that expected value of u given x is equal to expected value of u, and we know that expected value of u is 0 because on average the errors should be 0, right? Now we're going to say that instead of this assumption, let's use this assumption, because if I have this assumption, I can have this one for free, right? But the other way around does not work. So if I have the correlation is equal to 0, I cannot get back the mean independence. So here we're going to say that if the sample size is large enough, we are talking about the asymptotic properties of OLS. If the sample size is large enough, I don't need this strong assumption. I only need to have that x and y are uncorrelated. Okay. So in plain English, what does this mean? This means that we don't need to have expected value of u given x is equal to 0. So it means that we don't need to say there is no relationship between u and x. So again, if I have this thing, literally I'm assuming that there is no relationship between u and x, between the average of u and average of x, right? And by relation, I mean any relationship, both linear and nonlinear. But here, by assuming that the correlation is equal to 0, correlation of or covariance of x and u is equal to 0, I'm assuming that there is no linear relationship between x and y. I think it was in one of our classes that we talked about that the correlation has something to do with the linear relationship between two variables. So for instance, if the correlation between x and y is exactly equal to 0, it means that x and y are not linearly related to each other. They can be perfectly nonlinearly related to each other, right? What was our famous example? We'll look at y is equal to x squared, right? So I don't have a pen here, so let me see. Maybe I can. Well, I'm recording on my desktop, so I cannot show it to you. But imagine I'm talking about y is equal to x squared. So this is my y equals to x squared, right? The correlation, if I go from -5 to 5, is going to be 0. But does this mean that there is no nonlinear relationship? The answer is no. Definitely there is a relationship. My y is exactly equal to x squared. So here, what I'm trying to say is that we only need to assume that there is no linear relationship between x and u. That's it. We don't need to make assumption that there is no any kind of relationship, both linear and nonlinear, between x and u. So this is a weaker assumption that we have. Okay. So this assumption is weaker than zero conditional mean assumption. All explanatory variables must be uncorrelated with the error term, right? If you use those Venn diagrams, this, in other words, it means that all your explanatory variables should be exogenous. They should not be contaminated with errors. So all these things tell you the same story. So explanatory variables should be exogenous, they should not be contaminated with errors, or the correlation between x and u should be equal to 0. All right. Now we can say something about asymptotic analog of omitted variable bias. Remember, from previous chapter, we talked about the bias. When we have omitted variable bias, we said that the omitted variable bias, that bias depends on two things, right? Beta 2 and delta 1. For example, we have a regression y equals beta 0 plus beta 1 x1 plus beta 2 x2. And for some reason, we're going to omit x2, okay? If I get rid of x2, if you're using that Venn diagram, we know that because when I omit x2, then x1 and errors are going to be correlated with each other. So x1 and errors. So the x1 is going to be contaminated with errors, and it's going to make my coefficient of beta hat 1 bias. And we talked about this thing a lot in previous videos, lecture classes. So make sure, if this doesn't make sense to you, make sure that you review our previous class that we talked about omitted variable bias. Okay, we said that that bias depends on two things. the coefficient of the variable that you're getting rid of, so beta 2, and the relationship between x1 and x2. So we show that, we summarize that relationship with delta 1, because what was delta 1? Delta 1 was when we were regressing x2 and x1. So delta, you can think of delta 1 as a correlation. At least the sign of it is exactly the same as the correlation between x1 and x2. And we said that, okay, if beta 2 is positive, correlation between x1 and x2 is positive, you have positive bias. If beta 2 is positive, correlation is negative, you have negative bias, and etc. We look at some examples, right? So we say that, for instance, we are regressing wage on education and age, right? We know that education and age are positively correlated, so we are here. Let's say in this example, I get rid of age. We cross age. So what do you expect to see in terms of the sign of beta 2 if I have age in the model? So as age increases, wage is going to increase as well. So beta 2 is positive. So beta 2 is positive. The correlation between age and education is positive. So if I omit either age or education, we're going to end up with a positive bias. Okay. So, but remember, we said that unbiasedness is a property for any sample size. Now, in this chapter, we are interested in the properties of, in the asymptotic properties when the sample size is very large. So we should not use the term unbiasedness. We have to use the term inconsistency. So unbiased is the same as consistent. Bias is the same, or when I say the same, I mean analogous to inconsistency. So in regression analysis, we can safely say that whenever your coefficient is biased, it's going to be inconsistent as well. Okay, so it can get very technical, so because it does not apply to any kind of random variables. So for instance, we can have random variables that are biased but they are inconsistent, or they are unbiased but consistent. But I don't want to get you guys confused. For regression analysis, only for regression analysis, when we are talking about the beta hats, if in the random variables is the beta hat 1, beta hat 2, beta hat 3, whenever your coefficient is biased, it's going to be inconsistent as well, to keep it simple. Okay, so there is no omitted variable bias if the omitted variable is irrelevant or uncorrelated with the included variable. So we talked about this one in previous class as well. So if it basically says that if this variable that you're omitting is not correlated, or it's with y, or it's not correlated with x1, again, either it's not relevant or it's not correlated with x1, there's not going to be bias. So either if beta 2 is equal to 0 or delta 1 is equal to 0, bias is going to be 0. Now let's talk about inconsistency. For these are the large sample properties. For inconsistency is defined as p-lim of beta tilde 1. It can be beta hat 1. I just use tilde to distinguish it from unbiasedness. So we are going to say that p-lim of beta tilde 1 is going to be equal to beta 1 plus beta 2 delta 1, right? So this means that the inconsistency is equal to beta 2 delta 1. Because when a random variable is consistent, let's go back to this slide. When a random variable is consistent, the p-lim of beta hat jn is equal to beta j. So here the p-lim of beta hat 1 is not equal to beta 1. Look at that. The p-lim of beta hat or beta tilde 1 is equal to beta 1 plus something. So this something is called our inconsistency. So it is it's very analogous to the bias in any sample size, but in large sample size we call it inconsistency if you're talking about asymptotic properties, right? For practical purposes, we can view the inconsistency as being the same as the bias. Okay, guys, I want you, if you want to quote me somewhere, just be careful. Only in regression analysis and for practical purposes, whenever we have a biased random variable, or when beta hat 1, beta hat 2 is biased, it is going to be inconsistent as well. And of course, when it is inconsistent, it is going to be biased as well. That's the case only for beta hat 1. In general, this rule does not apply for any kind of random variable. But for your class, for homeworks, for for whatever you're learning in this course, you can think of inconsistency and unbiasedness as two similar terms. The only difference between the two is that inconsistency has something to do with the asymptotic property. Unbiasedness has something to do for any sample size. So that's the only difference between the two. Okay, let's go over an example. For example, if beta 2 is positive and x1 and x2 are positively correlated, then we say that the beta tilde 1 is positive, the inconsistency is positive, or we say it's asymptotically positively biased. So it has asymptotic positive bias. If beta 2 is negative, correlation is positive. So we have asymptotic negative bias, or we have negative inconsistency. If you're here, if beta 2 is negative, correlation is negative. So we can say we have asymptotic positive bias, or we have positive inconsistency. Okay. The difference is that inconsistency is expressed in terms of the population variance of x1 and the population covariance between x1 and x2, while the bias is based on their sample counterparts. Again, think of it this way. Whenever we are talking about unbiasedness, that's for any sample size, right? This is for any sample size. Now, if I have the luxury to increase the sample size and eventually send it to infinity, which means send it to population, so if the sample size is very large, at the end, I'll get the population, right? Then we're talking about the properties of the population, right? So this is a population covariance, not the sample counterparts. So I hope you get the idea what's the difference between inconsistency and unbiasedness or bias. Again, for practical purposes, you can treat them the same. Just be aware of the difference. One is for any sample size, the other one is for a large sample size. Now, finally, let's summarize the asymptotic, well, some properties and introduce something called asymptotic normality of our beta hat J's, right? So every single of these bullet points needs an explanation. In practice, the normality assumption number 6 is very often questionable, right? Because we said that this assumption is a strong one. We didn't like it. So we are saying that, first of all the unobserved factors and your explanatory variables are independent and they're strongly independent. And on top of that, they're normally distributed. Why do you think that they're normally distributed, right? There is no reason that to make that assumption. So because of that, we need to get rid of it. So if assumption, but let's see why we need assumption number 6. If assumption number 6 does not hold, then the result of T or F stats may be wrong, right? So let's go back here. If I don't have assumption number 6, what does this mean? It means that I can say only something about the expected value of beta hat J and the variance of beta hat J, right? I have no idea what is the shape of the distribution because I don't have assumption number 6. If I have no idea what's the shape of the distribution, then how can I rely on the T stat or F stat? Because we need these shaded areas, right? In order to do hypothesis analysis. If I don't know the shape of the distribution, I cannot do any kind of hypothesis analysis, right? I cannot do F test, I cannot do T test, I cannot construct confidence intervals. And guys, be careful. When I say that I cannot do, it means that it's wrong to do that. You can go ahead and calculate F test, you can go ahead and calculate T test, you can go ahead and calculate confidence intervals, but you cannot rely on those numbers because this assumption, if you don't have this assumption. So this is a critical one. So if you don't have assumption number 6, we cannot say anything about hypothesis testing, right? Fortunately, we are going to say that the F test and T test are going to still work if the sample size is very large. Okay, so why that's the case? Because of the central limit theorem. So, and also OLS estimates are normal in large samples even without assumption number 6. So let's say what's going on here. We're going to say that, going back to this whiteboard, we say that even if I don't have this assumption number 6, but my sample size is very, very, very large, then the distribution of the beta hat J is going to be normal, right? It's not even T, it's better than that, it's normal. So if I know the shape of the distribution without making assumption number 6, then I'm done. I have expected value, I have variance, I can calculate the T stat, I can calculate the F stat, I can calculate the areas under the curve, so I can do confidence intervals, and then I can do anything because this guy is normally distributed. Now let's see why the distribution for beta hat j is going to be normal even if I don't have assumption number 6. So we're going to use something called central limit theorem. If this is the first time that you're seeing central limit theorem, so let's click on this link and let's visualize it. So this is a website called Seeing Theory, and it's a very interactive and useful one. You can play around with with random variables, discrete continuous. You can play around with all these things, law of large numbers and etc. But now let's go over the central limit theorem. Again, what's the goal? The goal is to say if the sample size is large enough, the distribution of your estimate is going to be normal regardless of the distribution of the population. This is a very big claim. So basically I'm saying that whatever the distribution of u is, it can be, I don't know, it can be chi-square, it can be t, it can be f, it can be normal, anything. I don't restrict it to be anything. It can be a weird shape, hump shaped thing with 2 humps and things like that. Regardless of the shape of the distribution of u, I'm going to show it to you that the distribution for my beta hat j, the estimator, is going to be normal. So this is a big deal. This is a very powerful property that we're going to explore. Now let's visualize it using that link. Okay. Imagine, this is my parents' population. I'm gonna make some draws from this population, and I can make it as weird as possible. So for instance, I can make it like this, something like this. Very, very right skewed, right? It may be even worse than that. Okay, now let's draw one sample. And here I'm going to show you the central limit theorem. When your point estimator is average, in regression analysis your point estimate is beta hat, right? So if it holds for average, we are going to say that it's a general rule. It's going to hold for any kind of point estimator, okay, or any kind of estimator. So here, let's say the sample size is 1. Let's do one draw. So it means that I'm going to pick one draw from this distribution. So it means that if I want to, I don't know, select one sample, I can draw it from here, from here, from here, from here, and etc. Right? So let's do one. Okay. So, and I look at that draw and take the average, because I'm going to say that the x bar is going to be normally distributed regardless of the shape of the distribution for the parent, right? So this is one draw. I take the average. This is the distribution. We're going to look at the frequency table distribution. Okay. Let's do another draw. So this is a distribution. Let's do another draw. This is a distribution, and etc. Right? But now let me increase the sample size. If I increase the sample size to 15, so it means that I'm going to pick 15 of these observations and then take the average and report it here. Right? So let's see that. 15 of them, this is the average. Let's do another one, 15, take the average. Let's do another one, 15, take the average. Now, let's increase the draws to 50. So this means that we are going to draw 50 sample of size 15 from this parent distribution, and then take the average and look at the distribution for x bar. Okay, look at that. So if I keep doing this, if the sample size goes to 100, 200, we are going to say that it's going to be very close to normal distribution. What is the theoretical distribution? This is our theoretical normal distribution, right? So if I keep doing this, and if I had the luxury to increase this number of draws and number of sample size to, let's say, 100, 200, this is going to be perfectly normally distributed, right? But the beauty of it is, look at that, regardless of the shape of the distribution of the parent. So even if it is something like this, right? Let's see, 1 and 1 is even uniform distribution. It's very close to, I don't know why it doesn't, well, anyways, it's close enough. So this is uniform distribution. Even if I draw the samples from uniform distribution, the average is going to be normally distributed. Can you see that? This is very powerful. So what does the central limit theorem imply? It says that regardless of the distribution of the population, right? So this is my parent distribution or the population distribution, whatever shape it has, regardless of that shape. If your sample size increase, then your x bar, your point estimate, is going to be normally distributed. Okay. So now here, instead of x bar, we're going to replace x bar by our beta hat j's, right? So we're going to say that regardless of the shape of the distribution for these residuals, it can be anything. The distribution for beta hat j is going to be normal because of central limit theorem. Okay. So that's what we're saying. And again, if this is normal, then I need to have this assumption. I completely get rid of this assumption, and I use assumptions from number 1 to 5, and I say that, okay, I can calculate T, F, hypothesis testing, and etc. I can rely on those numbers. Okay, now what is theorem 5.2? This theorem is asymptotic normality of OLS. So it says that under assumption from number 1 through number 5, then look at that. Beta hat j minus beta j divided by standard error of beta hat j is going to be asymptotically, this is how you read it, asymptotically normally distributed with average 0 and variance 1. Okay, this is big deal. In last class, we saw that this beta hat j minus beta j divided by standard error of beta hat j was normally distributed if sigma was known. If sigma was unknown, it has a t distribution. So that holds for any sample size. But if the sample size is large, is very large, we don't need to have assumption number 6, and we know that it's going to be asymptotically normal. Again, it's a big deal. So we say that in large samples, the standardized estimates are normally distributed. Okay. Also, we're going to say that sigma squared is our consistent estimator for our sigma hat square. Sigma hat square is going to be our consistent estimator for sigma square. Because remember, this sigma is unobservable, right? And regardless of the sample size, we needed to estimate this guy. And we said that let's put a hat on top of it. And we proved that, in previous chapter, that expected value of sigma hat square is equal to sigma square. So that means that sigma hat square was unbiased. Here in this chapter, we're going to show that for asymptotic properties when the sample size is large, this sigma hat square is also consistent. So in a nutshell, sigma hat square is a consistent and unbiased estimator for sigma square. Okay. And finally, what do we have in the last slide? It says that in large samples, the t distribution is close to normal, right? Does that make sense? So this is not surprising. We know that if the sample size increases, t goes to normal distribution, right? And as a consequence, t-tests are valid in large samples without assumption number 6. So we said that if you want to rely on the answers of T, F confidence intervals, you have to have 6 assumptions. But if the sample size is large, you can get rid of assumption number 6, and you can still rely on the answers for t-test or f-test or confidence intervals. The same story is true for confidence intervals and f-test, right? This is important. Assumptions from number 1 to number 5 are still necessary, especially the homoscedasticity one. Sorry. Okay, so whenever you want to rely on your t-test or f-test or confidence intervals, you have to have the first 5 assumptions. Okay. Actually, for any sample size, you have to have 6 assumptions. For large sample size, you can have 5 assumptions. So that's the difference. Especially homoscedasticity. Think about it. If your data set is suffering from, if your model is suffering from heteroscedasticity when the sample size is 100, the heteroscedasticity is not going to go anywhere if you increase the sample size. So if you have heteroscedasticity when the sample size is 20, it's going to remain heteroscedastic when the sample size is 1 billion. It really doesn't matter. So, sample size, in short, the large sample size cannot bail you out on something like heteroscedasticity or bias. So we said that if your model is suffering from, you have omitted variable bias, or we have heteroscedasticity, regardless of the sample size, we're going to have omitted variable bias and heteroscedasticity. The only thing that the larger sample size can help you with is when you have multicollinearity. When we have multicollinearity, then if I increase the sample size, the multicollinearity can go away because the sample size is increasing, OLS is using more information, and it's going to have less and less hard time to figure out to pin down the beta hat J. Okay, so that's the only thing that you can take care when you have a large sample size, right? Remember that code that I said, give me large sample size, I can prove anything. Because if sample size is large, I know that the variance is going to shrink at what rate? At the rate of 1 over n. And so this means that the variance of beta hat J is inversely related to n sample size, and it's inversely related to, and standard error is going to be inversely related to square root of n. Okay. So what it means that if sample size increase from 10 to 1 million, your variance of beta hat J is going to shrink at this rate, and standard error is going to shrink at this rate. This is very good news, right? This means that if you have the luxury to increase the sample, this is a luxury, guys. Pay attention, because go back to the real world. You only work with one sample size, one sample actually, and the sample size is fixed. So let's say I give you a data set from Wooldridge package, and the sample size is 1,000. So for your projects, you don't have the luxury to increase the sample size. If I could increase the sample size, I had no problem. I said that, okay, increase the sample size so much that the variance of beta hat J is going to decrease and decrease. This is very good news, because when I calculate the t-stat, this standard error shows up in the denominator, t-stat is going to increase, and then that means that I can reject anything, because big T's are good. Okay, I can reject the null hypothesis. I can come up with, I can put any explanatory variable in the model, and I can throw millions of records of data into that model, and I can prove that that variable that I put there is relevant. So it can be as funny as something like this. I'm regressing wage on education, age, and people's eye color. We know that people's eye color is not relevant. So maybe when the sample size is 100, the model says that, okay, it's not significant. But if the sample size is 1 billion, I guarantee that the model is going to tell you that it's significant, because the variance of beta hat J is going to be super small, and when this is super small, the t-stat is going to be super large.